This is Algebra 2 at Trig, Unit 6 review. So we're looking at the 7th root of 48 to the 4th power. Rewrite the expression using rational exponents. So all we're trying to do is turn this into a fractional exponent, which would be 4/7. You could probably break that down, but right now we're just working on rational exponents and the radical notation. So here, because it's an odd index, it's okay to have a negative radicand. This is in fractional exponents, so we're going to write it with a radical. Same thing here, the 5th power, or the index of 5, 104. The 3 could be inside or it could be outside. Essentially it means the same thing. These we're going to evaluate without using a calculator. I know that the cubed root of 8 is 2. So if you have a negative exponent, that means to put the 2 on bottom with the positive exponent. And 2 squared is 4, so it's 1/4. This has a rational exponent, so it also means the square root. The 2 would be your index. We don't typically write the 2. Since I know what the square root of 16 is, I'm going to write with the 3 on the outside, because the square root of 16 is 4, so 4 cubed is 64. This is the cubed root. It's cubed. It's an odd index, so it's okay to have a negative. I know what the cubed root of 64 is. So the cubed root of negative 64 would be negative 4 to the 4th power. Four to the 4th power should be 256. Remember, when you're raising a negative to the power of 4, you would get a positive result. This is a negative exponent. The negative exponent's affecting the fraction. So now we could write this as 81 to the positive 3/4. And then you're looking at the 4th root of 81 to the 3rd power. You could say 81 times 81 times 81 and then take the 4th power of that, but I don't know what those big numbers are. We're not using a calculator for this. So I know that 9 times 9 makes 81, but we want 4 items that make that. So 3 times 3 and 3 times 3. So 3 to the 3rd is 27. So here we're looking at two bases that are different. If the bases are different, we can't add exponents. So if the bases are different, we need to somehow make them the same. I can't turn the 5 into a 25, but I can turn the 25 into looking like a 5, because 5 squared is 25 to the 1/3 power, and 5 to the 2/3, all raised to the 6th power. So 5 to the 2nd power to the 1/3 would be 5 to the 2/3, and this is 5 to the 2/3. So 5 to the 2/3 and 5 to the 2/3 is 5 to the 5/3. Now we can multiply in, and 5/3 times 6 would give us 30/3, which is 5 to the 10th power. On this side, we're looking at the 4th root. So we're looking at things that are 4 of a kind. 48 breaks down into 6 times 8, x squared, y to the 4th, y to the 2nd. I'm trying to break it down into groups of 4. Z to the 4th, z to the 4th, and z to the 4th. Three times 2 makes 6. 2 times 2 times 2 makes 8. We still have x squared, y to the 4th, y squared, and z4, z4th, and the z to the 4th. So here we have a group of 2's that would come out. We have a group of y's that would come out. And we have 3 different groups of z's that would come out. Don't forget your same index all the way through. So what we have left inside is 3 x squared y squared. Sometimes it's possible to simplify some of this, but because the 3 is to the 1st power, that doesn't simplify down. X squared to the 4th could be reduced, but 3 can't. So we're just going to leave it. This is the square root, so we'll be taking the square root of 4 times 5, because that's 20. We have an x squared with an x, and we have a y squared. That's in the numerator. The denominator has a 9x z cubed, which is a z squared and a z. So I know the square root of 2, or the square root of 4 is 2. I'd have an x, I'd have a y, I'd have a 5 and an x left inside. Down here I'd have a 3, I'd have a z, and I'd have an x and a z left over. So these 2 z's, I could have reduced them here. Maybe that would make more sense to reduce them in this case. But these x's would cross off and we'd be left with 2xy to the 5th power, 3z, the square root of z still down there. Now we'd have to rationalize having that z on the bottom. So I'm going to multiply by the square root of z and the square root of z, which leaves me with 2xy square root of 5z over 3z squared, because z, the square root of z times the square root of z is z. I already have one in there, so that's z squared. To add these 2 together, they can't be added together the way it is because the radicals are not exactly the same. They have the same index, thank goodness, but but they don't have the same radicand. This is the third, or the cubed root, the third root of 5, plus 4 times the cubed root. Well, this would be 5 times 5, which is 25, times 5, which is 125, times 5, which is 625. So we're looking for 3 of a kind. And when you bring that 5 out, it multiplies whatever is out there. So there's a 4 out here, so I'm going to bring the 5 out. It's going to become a 20. And now I'm going to have the cubed root of 5 left over. Now my radicands are exactly the same. So I can say that I have 26. I'm sorry, this should be a 3. Because my index was both 3, so they both need to be 3s. My radicands turned into a 5. They're both 5s now. So this is the cubed root of 5. On the second page, we're looking to add and subtract different functions. So we have the f function, which is 2x squared minus 3x, and we have the g function, which we're adding 3x minus 2. Well, a positive 3x and a negative 3x, they're going to cross each other out. You're going to be left with 2x squared minus 2. You could factor a 2 out of there, but we're just trying to group like terms together, so that doesn't help much. Perform the indicated operation and state the domain. Well, the domain for the first function, for the f function, would be all real numbers. For the second function would be all real numbers. So the domain for this guy would also be all real numbers. When we subtract, we're going to take the f function, which is x squared minus 3x, minus the function of 3x minus 2. You have to distribute that negative through to get 2x squared minus 3x minus 3x positive 2. So we're left with 2x squared minus 6x plus 2. And because the domain is all real numbers for both of them, the spot where they're the same is everywhere, so the domain is still all real numbers. We're going to multiply 2x squared minus 3x, 3x minus 2. So we're multiplying two binomials, so this is where we're going to FOIL together. So we get 6x cubed minus 4x squared minus 9x squared plus 6x. Leaves us with 6x cubed minus 13x squared plus 6x. Again, the domain would be all real numbers. In this fraction, we're going to take the f function and divide it by the g function. Factor out your x. Sometimes that can help reduce something, but in this case that did not reduce anything. That's a good habit to have, but nothing crosses out now. So all real numbers for your f function and all real numbers for your g function. So our domain is going to be all real numbers, except remember, you can't have a 0 in the denominator. So what makes the denominator 0? So if x equaled 2/3, then the denominator would be 0. So we say all real numbers except x equals 2/3. Now we're going to do the composite of f and g. F of g of x. So we're going to take our f function and we're going to plug the g function inside of it, which is 3x minus 2. So we're going to take every x that is in the f function and plug this 3x minus 2 into it. So we have 2 times something squared minus 3 times something. That is 3x minus 2 and 3x minus 2. We place the 3x minus 2 into each x of the f function. Now we have to FOIL this guy together, which is 3x minus 2 and 3x minus 2 minus 3 times 3x minus 2. So this is going to become 9x squared we're going to get negative 6 and negative 6 to give us a negative 12x and a positive 4. This will give us a negative 9x and a positive 6. 18x squared minus 24x plus 8 minus 9x's plus 6. And to collect our like terms, we'd have 18x squared. Our like terms are negative 24 and negative 9, which gives us a negative 33x. 8 and 6 gives us 14. So that's what f of g of x is. Now what is g of x? So we're going to take our g function and plug in our g function into that, which is 3 times something minus 2, and we're going to plug 3x minus 2 into that. So we get 9x minus 8. The cost in dollars of producing X sneakers in a factory is given by this equation. Looks like $60 per sneaker and some extra amount using the company. The number of sneakers produced in T hours is given by X of T equals 50T. Find C of X of T, and then evaluate what C of X of 5 would be. Okay, so we're going to take the C function and plug the F function into it. The C function is 60 times something plus 750. We're going to plug the X of T in there. So here it looks like we get 300T plus 75. So that should be C of X of T. Oh, I'm sorry. That should be a 50T, huh? So that should be 3,000. Alright, now we need to evaluate when T is 5. T is the part that's in there with the X, so the T value is 5. That's what our equation has. 3,000 times 5 plus 75. Well, 750 actually. I keep my numbers straight. So 15,000 plus 750, which is 15,750. See if we can make sense of what that actually means. The cost in dollars of producing X sneakers in a factory is this equation. That's the cost to make this many sneakers. The number of sneakers produced in T hours is given by this. Looks like they can make 50 shoes in an hour. So what's the cost compared to the number of sneakers that they make per hour? So what is the cost in 5 hours is what this is representing. That's the cost of making shoes for 5 hours. So verify that F and G are inverses of each other. So to do that, here's your F function, here's your G function. So we're going to do F of G of X which means we're going to take the 5 and plug the G into it and square that, minus 2. When you square a square root, you get what's inside. Then your 5's cross out. And we get the X like we were hoping to. Now we're going to do G of F of X, which means take your G function and plug your F function into every location there is an X. Well, here's the square root. The 2's cross out. The 5's cross out. And the square root is just X. So that helps support, because we got X for both of them. That shows that the two equations are inverses of each other. So, in this case, F of G of X, we take our F function and plug our G function into that. When we multiply it by 2, we get X minus 3 plus 3, which gives us just X. Down here, we're going to do G of F of X, which is taking our G function plugging in the 2x plus 3 in for its X. Distribute your half through, so half of 2 is just X, half of 3 is 3 halves, minus 3 halves again. They cross out just to give you X. So now we're going to find the inverse of 7x minus 6. So, in place of the f of x, we're going to write y. Then we switch the x and the y. Then we solve for y. So we add the 6 across. and we divide by 7. That would be one way to write it, or you could say 1/7 x plus 6/7. That would be another way to write that same inverse. So we could call this, just for notation purposes, f inverse of x. Over here, we're looking at this parabola, because it's x squared. I'm going to say y equals negative 6x squared. Then I'm going to switch my x and the y. I'm going to divide by 6, actually negative 6. And then I'm going to take the square root. Now, thinking this out, when we take the square root, we would typically have plus or minus as an answer. This here is a parabola that is upside down. We're only looking for where x is positive, so this is the part of the graph that we're dealing with. When we reflect that over the line, we're going to get our graph to come over this direction. So that's why we have a negative in here, is because we have to deal with negative x's. So that makes sense to turn it that way. We're still dealing with just the positive version of that. We don't want the negative version, which would curve down and come this way. So we want the positive square root.